So we're going to, as we usually do on a quiz day, just jump in, do some new stuff, talk about simplest radical form. Then we'll take questions on quiz material, and we'll do the quiz. The quiz, which covers that section on like graphing the trig functions, or that chapter on graphing trig functions, and integer exponents, the first section of the chapter we started last time. Okay. We have gone over working with radicals a bit last semester, so we're gonna just sort of continue with that. Properties of radicals. This is really just by definition. The nth root of a to the n is a. That's sort of how we define the nth root. We can combine radicals or split up radicals under multiplication and division. That's properties 2 and 4. If I take a root of a root, we multiply their indices, right? The index of each or the order of each. And that's really just an application of a property of exponents we already know. The radical, remember, is like the nth root is the 1 over n power. So if I were to write this in an exponential form, it would be a to the 1 over n, and then raising that to the 1 over m, because that's all in the mth root. And then if we multiply the exponents, we get a to the 1 over nm, and that's the nm root that we have right there. We're going to be real careful when we're working with radicals. Anytime I see addition or subtraction, slow myself down. Make sure I don't do anything rash. I don't want to regret it later. We can't split up radicals over addition or subtraction. So we're going to start with simplifying radicals. Basically, we want to take out any perfect nth powers. If it's an nth root, we take out any perfect nth powers. So here's a square root. We want to just take out squares. We start with factoring. There's two ways to think about this. 75 is 25 times 3. And then I could say, well, look, I could split up this radical. I'm choosing to factor it this way. And then I can split up a radical over multiplication. So I've got root 25 times root 3. And that's, of course, square root of 25 is 5. We end up with 5 root 3. That's nice. It kind of relies on us saying, oh, what's the useful way to factor it? Instead of factoring it as like 15 times 5 or something like that. But I think, for me, a more surefire way of reducing radicals is I just factor all the way. And then because this is a square root, I just need 2 of the same factor in order to take 1 out. So we still get 5 root 3. It doesn't require me to be clever, it just requires me to factor. I love being clever, but I can't always do it, so. Okay. So now we want to simplify this radical, the 6th root of 8. There's no 6 powers in 8, so you might be like, well, isn't that already simplified? So when we're simplifying radical, we want to take out perfect powers, but we also, if possible, want to reduce the order of the radical, or the index of the radical. So this is a 6th root. 8 does factor, right? It's 2 cubed. So this is the 6th root of 2 cubed. Now I'm going to take advantage of exponential notation. How would I write that as in exponential form and not radical form? Yeah, 2 to the 3 over 6. And now I'll just reduce, that fraction. That's 2 to the 1/2. And this is the square root of 2. That is simpler than the 6th root of 8. So on the next page, we have kind of just a procedure. I called it a procedure, but I don't know if it's necessarily fair to call it. I don't know if it really describes the procedure, but it just says what we want to do in order to make sure we're simplified. It's what we already mentioned remove any perfect nth powers, reduce the order of the radical if you can. Let's simplify this radical. It's a square root. So that means I could take out any perfect squares. I'm going to rewrite this as a squared times a times b squared. It's squares that get to come out of a square root. So here's an a squared and a b squared. They each contribute a single factor outside. So I have an a times b, and then what's left inside is just a. So I have ab times the square root of a. Questions on that one? Next, I've got a ninth root, and I mean, the only thing I can think to pull out right now is, I guess I definitely have y to the ninth in there, so I can see how I can pull out a y. But let's use the exponential form to kind of help us out through this. So 27 is 3 cubed. I'll start there. And then that ninth root is the 1/9 power. So I got 3 cubed, x to the 6, y to the 12, all to the 1/9. And we can distribute an exponent over multiplication. So that's what I'm going to do next. So I've got, when I distribute, when I raise a power to a power, we're going to multiply. So we have 3 to the 3/9 times x to the 6/9 times y to the 12/9. Now each of these exponents as fractions can be reduced. So we have 3 to the 1/3, x to the 2/3, y to the 4/3. If I've got a common denominator in the exponents, that means I can write them all under a single radical. I can write them all under a cube root. And I have 3 to the 1st, x squared, y to the 4th, and now that y to the 4th, actually, I'll write that as y cubed times y, because we could take out that y. You know, so this last step I took, I said, oh, I'm going to split up that y to the 4th as y cubed times y. That can be nice for like seeing exactly what we could take out. After you do a bunch of these, you might just look at that and be like, oh, there's a cube root, there's y to the 4th, so I could take one out and there's one left over. If you skip this step and just go right to that step, that's fine. It's not poor communication or anything. Questions on that one? When I looked at this, I had a feeling that using the exponential form and then distributing, I had a feeling that would be helpful because 9 and 3, 6, and 12 have a common factor, right? That's what made me think, oh, if I distribute, I'm going to end up with these fractions I can reduce and therefore be able to reduce the order of the radical. Ready for more? Okay. All right. Rationalizing the denominator. So we did this last semester. We did rationalizing last semester. We like to avoid, if possible, radicals in the denominator. That's more of a convention with constants, more so than with variables. But it is a convention. It's not like a thing that you're just not allowed to do. But it is more of a convention. We like to avoid radicals in the bottom, and we also like to avoid fractions inside the radical. So the first thing we do, if I see a square root or a radical, a fraction inside a radical is I split it up. We're allowed to split up radicals over division, so we could write this as root 2 over root 5. And who remembers how to rationalize the denominator? What do we do? Liz?
Times I find root 5 over root 5.
Yeah. So the problem is the root 5 that's in the bottom. So we'll just do times root 5 times root 5. Up top we have now root 10. On the bottom we have 5. Can we reduce that? We cancel the 5 into the 10? Why?
It's the root of 10.
Yeah, right. Yeah, one's in the radical and one's not, right? If you're going to be able to cancel it, they're either both in the radical or they're both outside the radical. That's as far as we go. If I'm rationalizing the denominator, and again, we could see in 615, we definitely need to do that. It pays to simplify the radical in the bottom first. You can start out by doing root 18 over root 18. That'll be fine, but you'll just have more simplifying to do later. So if we simplify this radical first, 18 is 9 times 2 or 3 times 3 times 2. So we got a pair of 3's and we can take one out. So now I've got 5 over 3 root 2. Now it's just the root 2 that's the problem. So I'm just going to zap the top and the bottom by the square root of 2. So now I've got 5 root 2 on top. What do we have on the bottom? 6. Yep, 3 times 2. How's that? These were both square roots. Now, we want to rationalize the denominator even if I have, say, a cube root or a fourth root. So I'm going to do an extra example here at no extra charge. This one's on the house. Let's say I've got 1 over the cube root of 9. Now, just multiplying by the cube root of 9 on the top and the bottom won't work, because then I'll get the cube root of 81, I guess, right? And that's not, 81's not a perfect cube. But what we want to do is just start by factoring. Cube root of 3 times 3. I've got 2 3's. If I had 3 3's, I'd be all set. So what should I multiply the top and the bottom by? Just the cube root of 3. I'm just trying to give it enough, just the right number of factors inside. With the square root, as it happens, because you need 2 of the same, right, to pull one out, it's always just that same radical, right, just zap it by itself. But when you have different indices of the radical, you just want to make sure you get to that number of the same factor inside. So we just need to pick up one more. So we multiply top and bottom by cube root of 3, so we end up with cube root of 3 over 3. One more quick one. If I have like 1 over the cube root of 12, 12 is 2 times 2 times 3. I want 3's. I want like triplets of constants, right, of factors rather inside. So I've already got 2 2's. I need one more 2. I've got a single 3. I need to pick up 2 more 3's. So what will we multiply it by? Say that again. And how do you get 18?
2 times 3 times 3.
Yeah. So we have the cube root of 18 on top. What do we have on the bottom? 6. Let's do another one. All right, I'm going to slow down. I see some addition happening inside the radical. I don't want to do anything I'm going to regret later. Definitely not going to split up that radical, right? What could we do?
Same denominator on one side.
Okay. Yep, so maybe I'll take that second term and write it as the fraction that it is. Negative exponents are a way of somebody trying to hide a fraction. So we want to bring it out in the open. So we have 1 over 2a squared plus 2 over b squared. You said same denominator, so the first fraction will have to pick up a b squared. The second one will have to pick up the 2a squared. So now the common denominator is 2a squared b squared. Up top we have b squared plus 4a squared. Now I have a single fraction, so what am I allowed to do? Split it up over division. I've got a radical in the bottom. I know I'm going to want to simplify that, rationalize, but first, let's simplify the radical. We have some squares we can take out, right? We'll take out an a and a b. So what we've got now is the square root of b squared plus 4a squared all over ab times root 2. And now we're almost done. Just multiply top and bottom by root 2. So I'm going to just combine that in a single radical up top because we can combine radicals under multiplication. So we have 2 times parentheses b squared plus 4a squared. And I'll leave that. You could choose to distribute the 2 if you want. I'm going to just leave it like that. And this is all over 2ab. That's as far as we can go. We cannot split up radicals over addition. By the same token, if I see this b squared plus, I can't pull the b squared out, right? I don't have a factor of b squared. It's just a term in there. So be really careful when you see addition and subtraction inside a radical. Questions? Okay. Let's take questions on quiz material.
We go over 2 and 3 on the practice quiz.
2 and 3 on the practice quiz. Yes. Can I see your practice quiz? Because I don't seem to have it. 2 and 3. Okay. So 2 is, oh, okay, yes, yes. Oh, actually, you know what? Hold on, let me just bring it up. On Canvas. Because I did post it. So we've got... So this says we have a function, and they say it's either a sine bx or a cosine bx. So they're telling us, when they say that, they're telling us there's no phase shift here, all right? And then we just want to know the specific function. So is it the sine or the cosine? Actually, given that there's no phase shift, that's probably the easiest one to figure out first. Is this a sine or cosine?
Cosine.
And how do we know?
It's in the peaks.
Because what?
Peaks.
Yeah, it starts out at the peak. What is A?
The amplitude.
Yes, but what is it numerically for this function? 0.5, and I know it's not negative 0.5 because it starts up at the top, right? There's no reflection. So far what we know is that it's 0.5 cosine of bx, and we have to figure out what b is. The value of b is related to the period of the function. What is the period of this function? to pi, right? Because that's when it hits the next peak. So I know that the period is equal to pi. So if the period is pi, then that means that 2 pi over b is equal to pi. Now, I guess it would be pretty simple looking at this to say, oh, that means b has to be 2 in order to cancel. But if you ended up with something that was more difficult to solve out, just what you need to do is just multiply both sides by b. And then we get, so those cancel, we get 2 pi is equal to pi times b, and then divide both sides by pi. So now the pi's cancel, and we get 2 is equal to b. So then for that problem, our final answer would be the function is 0.5 cosine of 2x. Sound okay? And then we're going to find the amplitude, period, phase shift. Okay, so negative 1/3 sine of 1/2 x minus pi over 8. When I see, so I know that there's a phase shift involved because I'm adding and subtracting in the parentheses. But the phase shift is not pi over 8, right? We can't just grab the phase shift until after we've factored out that coefficient on x. So I'm going to rewrite this first, factoring out the 1/2. Inside is x minus, and 1/2 times pi over 4 gives us pi over 8, so that's what goes there. Now I can tell that the phase shift is pi over 4, because it's just plain old x minus pi over 4 inside. Which direction? Right, yep. What's the amplitude? Mm-hmm. How about the period? It's not, well, it's not equal to 1/2, but that's the number we look at. How do I take that coefficient, the 1/2, and use it to find the period?
You have to put it under 2 pi. So
Yeah.
2 pi over.
Good. So 2 pi divided by 1/2, that's 2 pi times 2, or 4 pi. Now I think we have everything we need in order to do a sketch. So here's, oops, I need to leave enough room to do a phase shift. So let's say there's 4 pi. So this is 2 pi. There's pi and 3 pi. The phase shift is pi over 4, so that's like this amount here. So I'll first sketch it without the phase shift. I'll put that one in gray. It's negative 1/3, so it starts at 0 and it goes down, and then back up to equilibrium, then up at the peak, and then down. So here's a graph of negative 1/3 sine of 1/2 x. Now we're just going to put in the phase shift, move all of these over. So it looks like this. And I think that problem says, what are the x-intercepts? Yeah. So we could kind of point to them, right? There's one here, there's one here, and there's one here. Now this one is pretty easy because I just started at 0 and I shifted it over by pi over 4, so that's pi over 4. For the next one, when I shift to the right pi over 4, I'm just going to take each of these intercepts, you know, at 0, 2 pi, 4 pi, and add pi over 4. Right? If I were shifting it to the, I'm shifting to the right, so I'm adding it. If I were shifting it to the left, I'd just subtract the value. So 2 pi plus pi over 4 That's 2 pi over 1, so we get a common denominator. That's 9 pi over 4. 4 pi plus pi over 4. It's 4 pi over 1 plus pi over 4 is 17 pi over 4. So those are our x-intercepts. If you sketch one full period of sine, there's always 3 x-intercepts. If it's the cosine, I think if you sketch one full period where it starts at the peak or the trough and then ends at the peak or the trough, you end up with only 2 x-intercepts that you find, unless you sketch it out further. Other questions? If there aren't any other questions, you can let me know you're ready for the quiz by having stuff put away. Does anybody need a calculator or a pen?